Okay, next thing we're going to do is to get the initiators to log onto the network. So the initiators in our particular case, these are going to be the UCS Fabric Interconnect, which is going to be coming in from here. And then later we'll have the FCOE initiators that are the UCS to the 5K and also the converged network adapter to the 5K. But in the meantime, let's see, the 5K should have been rebooted. And let's now look at the show interface brief. Okay, it says now we have these 4 fiber channel ports. So let's go ahead and enable these ports. We're going to say on interfaces FC1 31 to 32. Those are the ports that go to the MDS switch. We're going to say the switch port mode is E for expansion and no shutdown. On the MDS switch, we're going to do the same thing on interfaces FC2 7 through 8. We're going to say the switch port rate mode is dedicated and the switch port mode is E. Now, once these interfaces actually negotiate, if we look at from the 5K's point of view and look at the show FCNS database, we should shortly see here that we're going to learn about the target in the storage network once the routing is actually converged. So let's look at the show interface brief. It says the port is up and trunking. And once routing converges, this is going to take a minute here. There we go. We now know that if someone wants to send traffic to this destination, this target, we need to route their packets to the domain ID 0x91. If we look at the routing table, which again is show FSPF internal route for vSAN1, it says I have 2 different routes. I have a route to switch 63. So from us here, if we look at the show FC domain list, locally I am switch number 58. So it's saying I'm 58. I have 2 connections to switch 63. These are specifically out FC131 and FC132. The cost of each of these links is $500. Switch 63 likewise has 2 links that go out to switch 91. Their costs are each $500, which means that my cost to the final destination, which is this here, would be a cost of $1,000. And I'm able to reach that by load balancing my traffic equally between FC11 and FC131 and FC132. But again, the point here being is that you don't need to configure this. It's automatically on the back end. They establish the fiber channel SPF adjacency. They assign themselves the fiber channel domain numbers. They exchange the routes. They exchange the fiber channel name server database, and we should automatically know who are all the initiators and who are all the targets in the network. Now, from a layer 1 configuration, there's not a lot other than that you would do beyond aggregating these 2 interfaces together, just like we would in the Ethernet world. And we talked about this within the scope of Fabric Path. Why would you run port channeling and Fabric Path at the same time? The reason is for routing stability. That if one of the member links of the channels goes down, it doesn't cause ISIS to reconverge in the case of Fabric Path. Same as here in the storage world, that if we take 2 fiber channel interfaces and port channel them together, it means that if one of the members goes down, it doesn't cause FSPF to reconverge. Now, from a storage world, the routing topology is much more delicate and much more important because from the upper layer protocol point of view, which is the SCSI reads and writes, those generally don't support retransmission. So if I'm doing a write to the database and I send the write and then there's a link failure, potentially the file system could get corrupted. So it's very important to make the network as stable and basically as static as possible, where the routing table is not very complex, and we basically only have one path from the initiator to the target. Now, from a configuration point of view of the channel, It's very, very similar to what we would see in the Ethernet world, where we're going to go to the interfaces and say the channel group, we'll give it a number, let's say, actually I don't think we have any channels configured now. Let's say show port channel usage. We do have some use. So let's say that this is channel group 128. And we'll say no shutdown. And same thing on the other side. Interface FC2, 7 through 8. Channel group 128. And no shut. If we then show port channel database, we should here shortly see that the member ports go from down to up. And it normally takes a minute for them to do the negotiation. So let's say show interface FC1 31 to 32 brief, suspended. Show interface FC1 31, suspended. I think they just need to be shut down and then brought out. So let's shut them down, no shutdown. There, trunking. Okay, now if we look at the show FSPF route, show FSPF internal route for vSAN 1, we should see here shortly after routing converges, the difference is now I have a single route between me and 5K8, and the cost is $250. So same exact logic here with Ethernet. We're basically just hiding from the upper layer protocol details that we have multiple physical links. Then we're going to do the load balancing based on the lower layers as opposed to based on routing. So between the MDSs here, we can still do equal cost multipathing between these two links, but if one of those goes down, it means that routing needs to reconverge. Where in the case of the SAN port channel, if one of those goes down, routing does not need to converge, so it makes the network ultimately more stable end to end. Okay, now as I was mentioning, the domain number here, the domain number is a 1-byte field, which 1 byte means that it has the possible values of 00 through FF in hex, or in other words, 0 through 255. There's a bunch of numbers out of this that are not valid, that are reserved ranges. So the effective number of domain IDs is much, much lower. It's like somewhere around like 50 or less in the network. So the end result is that as we start to add storage switches, like as we start to add 5Ks, as we start to add UCS fabric interconnects, because those devices are running fiber channel switching, each of those is going to have to be assigned a domain identifier, and they're going to have to run routing on the back end. They're going to have to run FSPF. So as the network starts to grow, eventually you go beyond the scaling limits of what the SAN is going to support. So as a workaround for this, they came up with a solution that you could think of it kind of like network address translation in the IP world, which is called node port virtualization and node port ID virtualization. Now, node port virtualization is also what we call fiber channel end host mode. And this is the mode that the UCS fabric interconnect is going to run in by default. What this means is that the fiber channel switch, the fabric interconnect, is not going to run any of the services behind the scenes, but it's going to act instead like an end host. So it means it's going to log into the network, it's going to get a fiber channel ID associated with it, and additional logins that come from the blades, from the servers behind it, the UCS is going to run as a proxy for those. So from the UCS point of view, this is going to be the default behavior that the links that are going up to the storage network, if we go to the CLI here, and we connect to NXOS, and we look at the show interface brief, And we are looking at interfaces FC11 and 12. These are the ones that physically go up to the MDS. It says that the mode for these, if we look at the show run interface FC11 to 12, the mode of these is NP, which means node proxy. Now, a node port, as I mentioned, is your end host. It's either your initiator or your target. A node proxy port, then, is one that is taking the node port's login and it is proxying it to the upstream device. So from a control plane point of view on the back end, in the UCS B series system, we have the blade and we have the virtual host bus adapter, the VHBA. The VHBA is going to send a fabric login that goes up to the UCS fabric interconnect. The fabric interconnect is going to take this login and it's going to proxy it and send it upstream to whatever switch we have connected into it. So either the MDS or the 5K or the 7K if we're doing FCOE. This means that the UCS in the middle is running the node port virtualization feature. The top switch is running the node port ID virtualization feature, which essentially allows us to have multiple fabric logins on an individual host-facing port. So from a configuration point of view, in order for the MDS to allow the UCS to log in to the storage network, we're going to be running the feature that is node port ID virtualization. The downstream device, which is the UCS, if we show run pipe include feature, they are going to be running the node port virtualization feature. So they're basically being treated as the host, and the upstream switch, the MDS, is the one that is listening for the proxy logins that are going to be coming from the downstream devices. So in our particular case here, the physical links on MDS1 that go to the UCS are interface FC2 1 to 2, and we're simply just going to say no shut on these. If we look at the show interface FC2 1 to 2 brief, we see that these ports are now configured as fabric ports, which again, fabric means it's the equivalent of an access port. It's facing to the edge of the network. And what we should also see, if we look at the show fabric login database, is that the UCS fabric interconnect now logged in on those two interfaces. So we assign them a unique fiber channel identifier each for one of the ports. If we look at the show FCNS database, the fiber channel name server database, it says that these two logins that occurred, it has the Cisco vendor ID, and these are node port virtualization hosts. So they're not actual initiators, it's basically just the switch in the middle that is proxying the login from the downstream device to the upstream device. So at this point, we essentially have the network connectivity in order to allow the UCS blade to talk to the storage array from a basic login point of view. Because the physical interfaces on the UCS, these are the node proxy ports, which are connected to the fabric ports on the other side. Then we have a fabric port connected to the node port on the FC SAN. The SAN would then be able to route this direction in order to get to the final destination. Now, before we do that, though, there's one other restriction that the storage network enforces. So we configured our ports, we got assigned addresses automatically, and we did a fabric login. The fiber channel domain services, things like FSPF, are running automatically behind the scenes. That's doing the routing for us. Then we logged in, we did a proxy login to the upstream switch that is running node port ID virtualization. Our very last step is that we need to tell the storage switches in the middle that we're going to allow a specific initiator to talk to a specific target. And this is what fiber channel zoning does. You can think of zoning as like an access list that is applied as a VLAN ACL in the Nexus or the Catalyst world. So by default, the switches are going to drop all traffic from all initiators, which is called hard zoning. Hard zoning means that you enforce in the data plane that you're going to drop the packets if there's not an explicit permit that says this initiator can talk to this particular target. Now, specifically, the way that we do this is by configuring what we call a zone and a zone set. The zone set is going to be the association between the initiator and the target. Now, in my particular case, on the fiber channel storage array that I'm using, there is a requirement of this. So let me actually log into the SAN. There is a requirement of the storage array of what the source address is of the initiator. And let's see, which one am I specifically looking for here? Let's say this value here. This specific value is the port worldwide name of the initiator. The port worldwide name of the target is the value that we saw on the switches. So when we go to the MDS and we look at the show fabric login database, and we saw on the port connected to the storage, this is the port number that they have assigned. The association of these two together on the SAN itself is what we call the LUN mask. LUN being the logical unit number, or basically the disk set. You can think of this kind of like a volume that the SAN is provisioning for the individual host, for the initiator. Now, the idea behind this is that if I have multiple different volumes on the SAN, let's say I have one that is for ESXi, I have one that's for Windows, I have one that's for a native Linux install. The potential issue is that each of those operating systems use different types of file systems. So VMware uses the VMFS, Windows uses NTFS, and so on and so forth. But from a bit level point of view on the disk, they have different formats. If Windows goes to mount the VMware storage, or Linux goes to mount the NTFS storage, there's potentially going to be a corruption of the actual disk, like of the boot record on the disk. So in order to prevent that problem, the storage array enforces its own level of access control that we call the LUN masking, or the LUN mask. Specifically, what I was looking at in the SANS config is the association between the initiator and the target. These are the two values that we're going to pair together in order to actually use the disks that we have configured on the storage. Now, from the network point of view, this is what we are going to configure as the zone, and then ultimately inside of the zone set. So you could think of this like as an access list that is specifying the MAC addresses of the sender and the receiver. It's enforced both on the switches in the middle through zoning, and it is enforced on the storage array itself through the LUN mask. So from a configuration point of view, I'm going to need to know both of these values. Okay, on the switches in the middle, the first thing that I'm going to do, so let's say like on the 5K, is in global config, I'm going to say that the zoning mode is enhanced for vSAN 1. Okay, what this means is similar to the previous example we saw with Cisco Fabric Services, and when I was advertising the role-based access control, the RBAC information from one switch to another. So I configured the role Brian on one of them, and then I committed the changes. I basically advertised the configuration from one switch to another. The end result is that I didn't have to configure the role on both of them. They automatically synchronize the information. This is what enhanced zoning does. It's basically the same as taking a VLAN ACL and advertising it to other switches in the Ethernet network. But in the case of Ethernet, there's no protocol to do that, so you would need to manually synchronize the access list on one switch versus another. But in the storage world, this is where one of the most operationally complex things comes in, is that depending on how big the SAN is and how many volumes or how many LUNs that you actually have created, you're going to have tons of mappings between these two addresses, between the initiator and the target. So instead of configuring these parameters over and over and over on every single switch, we're going to run zoning in enhanced mode, which means that we can simply advertise the zone set from one switch to another. Okay, the next thing we're going to do is to create an association between the two of these. We're going to create a zone set, and I'm going to say this is my vSAN1 zone set for vSAN1. Inside the zone set, I'm going to have a zone. This is like the difference between having the access list and having the access list entry. So in other words, the zone set can contain multiple zones, but when we go to apply it, we can only have one active zone set. It's like an ACL. When you apply it on the interface, you can only have one ACL outbound, one ACL inbound. Same here with storage. You can only have one active zone set, which is going to be enforcing the filters. So we're going to create a zone, and we'll say that this is my UCS to SAN. And the members of the zone are going to be based on the port worldwide name. So basically the equivalent of the MAC address. I'm saying that this initiator is able to talk to that target. So you're basically saying like the source and destinations. Okay, next I'm going to say that the zone set is going to be applied, and the name is vSAN1 zone set. This is the equivalent of applying the ACL to the interface. Then I'm going to save my changes, zone commit. Now once this is completed, if we go to the other switches, the MDS1 and MDS3, and we look at the show zone set active for vSAN1, we should see now that this information was automatically advertised between the switches by using Cisco Fabric services. So assuming that the switches are adjacent already with the trunk links, with the expansion ports, then if you make the zoning change on one switch, you should be able to save those changes, and then it gets advertised to all of the other switches in the network. So you can think of it kind of like how VTP works in Ethernet, that you configure the VLAN on one switch, it advertises it to the other one. But in this case, we're using it to advertise the association between the initiator and the target. Okay, then lastly, I'm going to configure the UCS to actually use the particular storage. So as we talked about this previously in the UCS class, what I'm going to do here is to log back in because I was rebooted. Okay, there's a question. Do you have anything like master client transparent like you do in VTP? For zoning, there's no roles between them. So any of the switches can make changes to zoning. If one of the switches crashes, the zone set is still saved in your running config. So if we go back to the switches, and let's say like on MDS3, if we look at the show run zone, those changes that I made are automatically stored in my local config. So even if the other switches go down, I'm still maintaining this. And when the switch reboots, it will reactivate the zone set that it has. Okay, what I'm going to do now is configure a very basic service profile with a boot policy that's going to use the information that we have from the storage array. So I'm going to do this fairly quick. We had already gone through this in the UCS class if you guys need to review that afterwards. So under service profiles, I'm going to say to create a new service profile. And I'm going to fill in just the most basic values that I need. I need a UUID. So I'm going to configure just any value here. From networking point of view, I'm going to say use no network cards, no VNICs. From the storage point of view, I'm going to create a, let's say, expert. I'm going to give the VHBA a node name, where this technically can be anything. I'm going to add a virtual HBA. I'll call this VHBA1. I'm going to give it a port worldwide name. But what is important about this is that this value is going to need to match what the storage array was configured for the LUN mask. So in a real deployment, what you would normally do is configure a pool of PWWNs on the UCS. When the blade gets assigned one, you then need to tell your storage administrators that you need to add this value into the LUN mask that's associated with the actual disk volume that's going to be created on the storage. So the point being is that this is a static configuration to make sure that no other initiators, no other servers basically can boot the disk that's on the SAN. So I think the rest of this I can skip. Then I need to go to the, I believe it's the server boot order. I'm going to, actually I'm just going to skip this. I'm going to finish. Then under the VHBA, or actually under the server, under the server I'm going to go to the boot order, and I'm going to modify the boot policy to say that, actually I'm going to create a new policy. Let's do this. Let's say modify boot policy. And a specific boot policy. Okay, so I'm going to specify how do I want this blade to actually talk to the storage. I'm going to say that on virtual HBA1, this is the one that I had created, the storage port. I'm going to add a target to this. And this number here, this is what the storage port is on the SAN. So VHBA1 says the target is that destination. Okay, so that should be, I believe, almost enough. I may need one more thing, which is I may need an IP address pool so I can connect to the KVM of the blade. Okay, so let's go to equipment. Let's go to the server, the Blade Series server. And I'm going to pick one of the blades, let's say server number 1. And I'm going to associate a service profile. So I'm going to add the profile that I had just created. Okay, then let's connect to the KVM. So what I'm looking for here specifically is we're going to get to a point where the blade goes to boot the OS from the SAN, and we should see on the BIOS screen, it should have an output that says the virtual interface card VHBA driver. and that's going to tell us whether the storage configuration is correct or not, which is this here. Okay, that there is the destination address of the storage array. So I believe it should successfully boot after the next step here. Okay, so in this case, on the actual storage array, there's an install of VMware ESX that was previously installed on it. What this is basically showing is that from the storage network point of view, we have connectivity from the initiator all the way to the target, and that the zoning is correct. That is essentially like, again, the ACL that's controlling how we access the targets. But what I wanted to show here is that now that the server is actually up, if we look at the show fabric login database, we should now see that there is a new login that came from the port worldwide name that I had manually configured on the boot policy of the actual UCS blade. So if we now look at the show FCNS database, we should see now that there is this initiator that is talking to the actual storage, which is the SCSI target. Now here it doesn't show the type here because this format here, I didn't follow what specifically the vendor code is. But the result of this here, where we see on the same physical port, there are multiple logins. This is what the node port ID virtualization, or the NPIV feature, is doing. So this means that from the UCS point of view, it's not making a routing decision on how we are reaching the storage. It's doing the connectivity similar to how it does in the LAN world, that we are doing a dynamic pinning for the virtual NIC to the outgoing interface. So for example, if we were to go back to the UCS Fabric Interconnect, and from the CLI point of view, and we were to look at the show NPV external interface usage, what this is the equivalent of, as we talked about previously in the LAN config of UCS, is the show pinning server interfaces, or the show pinning border interfaces. Where in the case of the regular Ethernet world, this would show the virtual NIC card binding to the upstream LAN interface. In my case here, it says that for the storage association, the virtual fiber channel 702 interface, this is the one that actually is on the blade, on the virtual host bus adapter. It is associated with interface fiber channel 1/11. This is the way the traffic is actually routing from the blade in order to get to the SAN. And we could also see this if we look at the show interface virtual fiber channel 702, that this should tell us that this is chassis number 1, slot number 1, the HBA called VHBA1. That's the string that I gave it. And we can see that it says the virtual SAN is up, which is the one that we're using. Just the default vSAN is number 1. There's a question: can I show this? Can I show the SAN port channel config again? It's basically just one extra command. There are other options that you can set, but I did it with the minimum configuration, which is just to say channel group. This is the equivalent of running a static port channel in the Ethernet world, like saying that the channel mode is on. Most of the time you would not want to do it this way though, because if there is a problem, the switches are not negotiating the channel, they're just statically hard coding it on. To do the channel negotiation, you would go under interface SAN port channel 128 and say the channel mode is active. This means that you're running the port channel protocol, which is the logical equivalent of LACP. But this is specific to Nexus and to UCS. It's not interoperable between the vendors. If you were to configure a channel on the UCS side, it does run the port channel protocol, so you would need to enable that either on the MDS or the Nexus side that it is channeling towards. There's another question: does the route cost change if a member of the port channel goes down? So let's say, I shouldn't have said channel active there. Let's say show FSPF route internal, or show FSPF internal route vSAN1. Then let's go to the member port like FC130, no 31, and shut that down. I think it purposely does not affect the cost unless you were to flap the entire link and then bring it back up. Because normally in the regular routing world, it would adjust the cost based on the underlying bandwidth. But with storage, you're more concerned about the stability of it versus the routing of it, like the path selection. So I could force it to reset by clearing the FSPF database, but that would basically be like clearing the routing table, so any of the storage that's transiting the links would be dropped.